We're very happy to have Siddharth Karamcheti visiting us, part two. Sid came a little earlier, but there were some issues with stomach bug. So we're very happy that he was able to come here and he's feeling well. Sid has done some great work at Stanford and at TRI working on language understanding and language-based learning for robotics. And that's what he's going to talk to us about today. So, take it away, Sid.
All right. Good morning. So thank you, Matt, for the kind introduction. My name is Siddharth Karamcheti, and I'm very excited to share my work today towards building and deploying interactive robots to work with us in the real world. To start, I'm going to channel my inner comic book nerd and turn back the clock to 2008 with a scene from the very first Iron Man movie. A scene where Tony Stark, Iron Man himself, is working with his collaborative robot arm dummy to construct what will ultimately become the first version of the Iron Man armor. I want you all to pay attention to what Tony says, how the robot responds, and where Tony's focus is throughout the flight.
Maybe mine can actually do some good. Next. Up. Not complete, dummy. Right here. You got me? Stay put. Nice. You're of no benefit at all. Move down to the top. I got this. Okay, I'm sorry. Am I in your way? Up. Screw it, don't even look. You are a tragedy.
So this was and still is the picture that I have in my head when I think about human-robot collaboration. And yet it's been almost 20 years later, and despite so much incredible progress in robotics and machine learning, I bet that most of us don't have systems like this in our research labs, let alone our workshops and homes. Why not? What would it take to build a system like this? Well, let's run it back and take a look at what Tony says and what a robot actually needs to do under the hood. Up first are instructions that are explicit, moving closer, or identifying and planning a path down to the table. To execute on these instructions, we need robots capable of embodied perception, an ability to understand and make connections about the world, and then use this understanding to inform action. But then there are the things that Tony says that require more than just a literal interpretation. Right? Next requires an understanding that we're trying to assemble this new mechanism. We just finished soldering one connection and now need to move down to the one below. The exclamation, "don't even move," isn't a literal "stop moving or else," but more like an "okay, get out of the way," but also "please don't touch the hot soldering iron and burn the workshop to the ground." Acting on these instructions requires some extra knowledge about the world, knowledge necessary for a robot to reason more deeply about its behavior. Taken together, these interactions fulfill a principle that I call capability, the fundamental tools a robot needs prior to being deployed. Now, while the clip hinted at some of what I meant by embodied perception and knowledge, I want to make these categories a bit more concrete and highlight some of the problems that I've tackled in my research. Consider this desk representing a simpler version of Tony's workshop and focus on the embodied perception piece, starting with what it means to build a visual understanding of our environment. Crucially, there are different levels of visual understanding. At the low level, it's a scan of the scene, separating parts from the table, getting a rough sense of textures and shapes. At the high level, it's mapping elements of the scene to names and meaningful concepts. Hey, this thing here is a 9-volt battery. That thing on the right is a soldering iron. And while ideally we'd be able to capture this full spectrum, prior approaches only tend to capture one of the two extremes, which hurt our ability to use these models for tasks that require blending low and high-level features. To tackle this, my early research identified language as a way to bridge these different levels. Let's say I start with this low-level understanding, and I give you a description of the image, a workspace with a red battery and a soldering iron. What happens? Well, if we look at lots of these image and language pairs, we can start to iteratively build connections, linking similar bundles of shapes to objects or other concepts mentioned in language. We can go even further. Let's also try generating these new language descriptions from the image alone. Descriptions like a soldering iron sitting to the right of the various components, or an electronics workspace for assembling simple LED circuits. Not only does this let us link to higher level concepts more explicitly, but it helps us build scene level connections that help generalization. The crucial part here is that we're really deeply weaving language into how we encode images, really modeling the nuance of how words and individual parts of an image interact, letting us build this robust understanding of new scenes. Now, building from embodied perception, we also want robots that can tap into other sources of knowledge to reason and plan behaviors. One example from the video is common sense reasoning, right? Just like avoiding the hot soldering iron. For this application, we might want more, like asking our robot to identify the 1,000 ohm resistor from this close-up. A question that requires background information about how to decode resistor values from the sequence of color bands painted on each part. One way to enable these abilities is through visually conditioned language models, or VLMs, one of the advancements of the past 2 years that I'm really excited about. A VLM takes as input an image and a text prompt and generates a text response. The model shown here, Lava, is one of the earlier and most popular open source VLMs that came out in early 2023. It consists of an encoder that maps images to the input space of a pre-trained language model and is trained by fine-tuning the language model end-to-end on labeled image prompt response triples. The surprising part is how efficient these models are. From a data perspective, you need less than 500,000 examples to glue these two modalities, image and text, together. And then once trained, these models start generalizing far beyond the scope of the fine-tuning data, handling new objects, scenes, and prompts with ease. Now, while this is a compelling recipe, I don't want to forget the context. Machine learning as a field, 2023 and now, is characterized by rapid and unpredictable progress. New models are released daily, and each show this tremendous ability, but they only capture a really narrow slice of the broader design space. This makes it really hard to build intuition for how we might change or tweak a model recipe for new scenarios. For Lava, this is maybe a bit more obvious if we peek under the hood. The language model they built from was a 13 billion parameter Vicuña 1.5, a chat model that was fine-tuned from Meta's Llama 2 language model. And the bulk of images they trained on came from a dataset called MS Coco, a collection of images from Flickr. I'm not actually sure how many people actually remember this website, that were all sourced prior to 2014. Now, looking at this, there are questions that different people might have. As a roboticist trying to run a VLM in a real-time setting, like how small of a language model are you going to get away? Can I get away with? Like, do I need all 13 billion parameters? If I'm trying to deploy this VLM to process COVID-19 tests, something that definitely didn't exist in 2014, how much new data would I need? Now, to answer questions like this, and to build intuition around VLM modeling choices, data, and scaling laws, we developed a framework that not only maps out the different design axes, but allows for systematic exploration. To do this, we first assembled an evaluation suite comprised of tasks measuring general reasoning, like sanity checks, in addition to specific targeted skills, like literally detecting objects. We then use these evals to help contextualize one-step controlled ablations, like swapping the 13 billion parameter Vicuña model with the 7 billion parameter variant trained on the same data. We're going a step further and seeing if simply extending train time with a smaller model, a fixed upfront cost, changes results. Now, one of the most important outcomes in running this study is that our empirical understanding of the individual changes, each given intervention, like doubling the number of train steps, that seems to transfer better and generalize better across different VLM families. This is especially important when we're interfacing with the broader ecosystem of models that are open weights but closed data, or even models that are served through restrictive APIs. Okay, so back to the start. If capability captures the expectations I have of my robot prior to deployment, then the next principle captures what happens after, actually putting robots in the world with real people. Throughout that original video clip, there are things that Tony does that start to hint at a level of fluidity, a sort of flow state he enters with the robot. He'll constantly interact with it, shaping its behavior through feedback that to us just feel natural. He'll physically halt the robot, expecting it to back away, or he'll use his voice, pausing and emphasizing to modulate the robot's behavior. Handling these types of multimodal interactions online, like during deployment, seems like another important part of the story. But the most powerful parts of the video to me are when Tony uses these interactions as a springboard for teaching new concepts and behaviors on the fly. Not only expecting the robot to correct its behavior, but relying on its ability to learn and reliably extrapolate from its feedback in real time. Taken together, these two pillars fulfill this principle I call sustainability, building robots that adapt and grow during deployment through natural interaction with people. To drive this principle home, I want to return to the question I asked at the very beginning. How might we build a system like that from the Iron Man clip today? A system that can enables these fluid interactions, a sort of flow state with the robot in real-time teaching. Now, one caveat is that I actually don't know how to build an Iron Man suit. I also don't think I have the approval to do it. But I do have another very nerdy hobby that might help us split the difference. That being stop motion animation. For the uninitiated, stop motion is a technique for filmmaking in which a director, me, is going to incrementally change and photograph a scene to build an illusion of motion. Now, while this example is relatively simple with a stationary camera, you can consider that for more complex films with more dynamic motions, like orbiting around a character or tracking them as they move, there's a need for more reliable and precise camera control, something that I've historically had a problem with because I have shaky hands. But it's perhaps something that a robot would be good at. Which brings me to Vocal Sandbox, a framework for building interactive robots that can learn new visual concepts, motion skills, and high-level behaviors by working alongside real people. So here, you're going to see my co-author Jen working with the robot over the course of a continuous 2-hour period to shoot a 1-minute-long stop-motion film shown on the top right. We're going to seed the system with the models we built earlier under capability, right? The vision models and VLMs for identifying and planning behaviors relative to key features in the environment. More than that, we explicitly allow for different types of multimodal interaction in real-time teaching. For example, teaching new visual concepts like the big Avengers logo, as well as entirely new motions, like how to orbit around a character, a motion that's taught and extrapolated from just a single demonstration. Now, I'm pretty proud of the system. It's the culmination of what I tried to capture throughout my PhD. And it's a system that I think truly highlights the pivotal role that language plays in learning for interactive robots. Okay. So in the rest of this talk, I want to dive more deeply into each of the different projects I highlighted. I'm going to start with embodied perception, providing more context around our approach of Voltron for learning multi-resolution visual representations with language. I'll then present our work investigating the design space of these visually conditioned language models, and some follow-up work on building vision language action models for robotic control. Next, crossing over to sustainability, I want to expand on Vocal Sandbox, highlighting the parts of the system that we found really important in enabling different forms of interaction and online learning. And then finally, I'm going to briefly zoom out to discuss my broader research agenda and some directions for future work. Okay, there are going to be these blue slides throughout, and for these, feel free to ask questions. Anyone? Okay, great. So I want to start this next part by returning to our visual understanding example from before and formalizing the setting. Our goal, very crisply, is to learn a model that maps an image to a set of vectors that encode what I'm going to call useful features of a scene. The hope is that by pre-training our encoder on large diverse data, we're going to be able to enable efficient transfer, using our representations as a starting point to fine-tune for specific downstream tasks. In this case, we're using our representations to encode camera observations for learning a robot control policy from a very small number of demonstrations. An important question here is the data that we're going to pre-train on. Now, because we care about embodied perception, especially for robotic manipulation, we're going to train our representations on a dataset called something v2, a moderately sized dataset comprised of people manipulating common objects, literally doing some verb with some noun. Now, earlier we defined the spectrum of visual understanding, ranging from the low to the high level. To make this more crisp, I want to highlight concrete robot perception applications that exist at different parts of the spectrum that kind of need different types of these features. Starting at the low level, in warehouse packing applications, we might want features that are useful for low-level graph segmentation. In more free-form manipulation settings, we'll rely heavily on systems that can understand objects and their affordances. And for broader human-robot interaction applications like assistive feeding, we want to capture higher-level properties of scenes. What are people doing, and how are things changing over time? And so multi-resolution representations, like a camera that has different levels of optical zoom, are those that capture the full spectrum of these features. And unfortunately, previous approaches fail to capture this, and instead they default to one of the two extremes. On one hand, we're going to have approaches like masked autoencoders that learn representations through reconstruction. We're going to erase part of an image and learn to fill in the blanks. This is going to encourage local pattern recognition, capturing properties like texture and shape. But there's more going on in this image. A person is peeling something in a kitchen with a ton of vegetables and other kitchenware around, which feels like global information that we want to be able to encode. Other approaches favor these higher level semantics, approaches like CLIP from OpenAI that learn to match images with captions. Now these lie at the other extreme. They encourage representations that focus on high signal bits, like objects and things that are easily described, like the foreground parts of an image. For example, clip representations of these two images are really close together because in both, someone's holding a carrot. But now we start to have the opposite problem. Focusing on the high signal bits starts to erase the important local information. And as a result, we find that the representation of this image of a dog is also treated similarly to the other two images, right? And both persons still technically holding a carrot. So instead, we want to strike this balance. And our key insight is that we can use language supervision to help bridge this feature gap. An insight we're going to push to every part of the representation learning pipeline. Specifically, we're going to craft an objective that balances conditional image reconstruction with language generation. To provide some more intuition, I want you all to consider reconstructing this image. And think about what you're spending model capacity on, right? Like I give you $50 of infinite model budget. What is that model? Like how are you spending that money? Well, there's some orange object in the middle of the scene and something that maybe looks like a hand. To generate the missing pixels, we're basically asking our models to consider the whole space of possible orange things that might appear with people's hands and reconstruct. That feels really hard. But now let's say I tell you that we're peeling a carrot over a counter. What changes? Well, that orange object is most likely a carrot, so we can knock that out. And if we're peeling something, then we kind of know what the area around it should look like. Similarly, I kind of know what kitchen counters look like, so maybe I can fill in the right side. In other words, language conditioned reconstruction does two things. It's going to let us tie words and phrases to individual parts of an image. And this is a very nuanced point, it's going to let us shift our model capacity to the harder parts of the image. The finer grained features like the exact positioning of objects relative to each other. Now let's move on to language generation. Given just the image, we're going to try and generate each word in this caption one at a time. This part of the objective lets us link to higher level concepts, objects, and affordances more explicitly in a way that strengthens connections and patterns at the scene level. It's also going to facilitate stronger forms of generalization, linking these features to semantically similar appearances throughout the dataset. Now, this simple objective, using language conditioning and language generation together, is the backbone of our approach. Greg.
Sorry. So just going back to you've discussed how adding the conditioning might change what the model focuses on, but arguably the biggest element which affects what the model focuses on is the loss.
Mm-hmm.
So the loss here is still some kind of pixel reconstruction loss.
So the loss here is a mixture of pixel reconstruction loss and for language generation, a cross entropy loss on the generation tokens.
I guess you haven't yet. Okay, so I will defer.
We're literally going to get right into it.
Sorry.
Yeah. So we're going to implement this framework. I called it Voltron in a straightforward way. Now, since we're training on something v2, which is a video data set, we're going to start with a multi-frame masked autoencoder. Again, this is our starting point to learn low features. And like Greg mentioned, the objective here is pixel level reconstruction. For the first part of the objective, for the language conditioning, we're simply going to add prefix conditioning, letting our model attend to the words peeling a carrot while encoding the masked images. And note that because we're using a transformer architecture to encode and decode these images, we can allow for variable length image contexts. For example, encoding a single image or a sequence of multiple.
So with this, do the masked regions not change over time?
So we're going to sample a new mask for every instance of an image or image context in our data set for each epoch. We're going to run 400 epochs.
But this is a video.
But this is a video, so within a video.
Within a video, for a given batch, mask is consistent across time, right? So we're not leaking information. Yeah. So for this, we're going to limit ourselves to 1 to 2 frame contexts that are just going to be sampled from that video. Now, to incorporate the second part of our objective, we're going to extend our model with an autoregressive language decoder, using our learned representations to generate the corresponding utterance. Now, note that we can't condition and generate simultaneously, right? Like we don't want to leak information if we're trying to generate the exact same caption that we're conditioning on. So instead, we're going to set a hyperparameter alpha that's going to act as a bias point. For each example in our data set, we're going to sample the path to take through the model just based on this value. Now, this is a limitation of our model. Like there's no free lunch here, right? While a naive value of alpha equals 0.5, just like a 50-50 coin toss, works well for our experiments, we're still susceptible to the two extremes that we talked about with prior approaches. For example, if I set alpha at a higher value, like 0.7, 5.8, we're going to emphasize learning the higher level semantics and erase low level features similar to models like that. But we still get more of this balance outright. And now after pre-training, we're going to use just the encoder to kickstart fine-tuning for downstream tasks. Now note that we get something a little extra from our model just because of the way it's structured. Because we train with language conditioning, we can also provide, in addition to the image representations, multimodal representations that kind of mesh together the language features with image features. It's going to be especially important in a little bit. We're going to evaluate our learned representations on a range of tasks requiring these different types of visual features, from the examples on the earlier slide to other tasks like learning robot control policies in the real world, or modeling a person's intent over time. Crucially, we're going to show that our representations not only uniformly outperform prior approaches across the board, but they do so by training on much less data, a huge win for compute efficiency. Now, I want to highlight one of our cooler experiments, evaluating Voltron representations on detection from referring expressions. Right, so given the image and the language description, the blue-black pen on the front left of the orange can actually predict the bounding box around the corresponding object. The evaluation data set we use is called OCID-REF, and it's nice because it splits scenes to different categories based on amounts of clutter. From minimum cluttered scenes containing fewer than 5 objects to maximum cluttered scenes containing upwards of 15. Now, I want to call attention to the performance of Voltron relative to CLIP and masked autoencoders, baseline models that are trained on 2 to 3 orders of magnitude more data. Again, Voltron is only trained on about 500K images sampled from these video clips, while CLIP was trained on 400 million images. Now, the primary reason for these gains, and something that I find really important about this work, is the fact that we're able to learn these detection models directly from these multimodal representations that have already learned to weave together languages and images in the right way. Now, this isn't the case for CLIP or the masked autoencoding models. For example, in CLIP's case, while we're still learning with language, we're not actually learning this fused enmeshed feature space. We're learning 2 separate models, one for representing images and one for representing text separately. Now, to drive this point home, I actually want to show you how simple it is to actually define the detection model we're using for these tasks on top of a learned Voltron encoder. So this is some PyTorch code, but the flow is actually pretty simple. We're just going to feed the image and text prompt to Voltron and pass the resulting fused embeddings to a lightweight MLP that just maps this to the 4 coordinates representing the bounding box coordinates. This simplicity, especially compared to how we might typically build a language condition detection model in the vision literature, is not only really refreshing, but it hints at the broader impact of this work, the right way to incorporate language for multimodal tasks. Okay. Questions? Great. Now, while Voltron showed us how to use language to learn these more holistic visual representations, it only scratches the surface of the types of tools our robots might need for the real world. So in this next part of our talk, I want to build on the principle of capability we defined earlier and work towards learning models that can incorporate other sources of knowledge to reason and act in the world. I'll start by returning to our schematic of Lava, one of the more popular visually conditioned language models, or VLMs, and fill in some more details. Now, recall that the key idea with the VLM is to map images, specifically image representations, into the input space of a pre-trained language model. The idea is to treat these representations as like soft tokens, basically put them in the same space of the space of token embeddings that a language model will learn over text. We're then going to fine-tune the language model on a fairly small data set of image prompt response triples, resulting in a model that can answer questions, chat, or otherwise reason about images. Now, like I mentioned before, each new model that comes out only tends to capture one set of design choices, making it really hard for us as researchers to build intuition for how to change or tweak a model for new applications. I want to dig further into some of the design choices that Lava made to help us start to ask questions and map out the different axes that might matter in building VLMs more generally. Right, so we talked about this before, but the language model they chose to build from was the 13 billion parameter Pecunia 1.5, a chat-tuned language model derived from Llama 2. Why 13 billion parameters? Could we have gotten away with a smaller model? Also, why use a chat-tuned model versus a base LM, one that hasn't been subject to the same amount of instruct tuning? The image encoder used in the initial work was CLIP, which immediately should feel strange given what we just learned with Voltron. Right? What about reasoning requiring a fine-grained understanding of the scene? Going a level deeper, and one of the silent failures that led me to do this work in the first place, and I seriously could talk about like this one point forever, was the default image processing scheme. So most of the visual models, or most of the image models we train or we use, expect images to be square coming in at a fixed resolution. If your image isn't square, And most images aren't, right? This is a 16:9 aspect ratio. Your phone will shoot 4:3, 16:9, or ultra wide. Robotics data is also like 640 by 480 pixels. The default approach, though, for this model is to resize the image to the appropriate scale. So take scale down the shorter side of the window and just chop off either end until it's square, literally losing information. It feels suboptimal.
Maybe a stupid question, but these models are transformer models usually. Why do they care about they could deal with any aspect ratio?
So they could deal with any aspect ratio. And this is actually a question that I don't actually have a single answer for, right? But there's tons of historical reasons for why we want square images, right? So early ResNets with Caffe or TensorFlow static graph models, we didn't want to deal with the dynamics of flattening out images or image representations in different sizes. Now you're absolutely right. They shouldn't care. It's still something that these models tend to expect.
And if you
Meaning if you don't, yes.
if you give so they can train on square, and if you give them rectangular, they break.
Yeah, you give them rectangular, they break, right? Just the type signature doesn't match up.
Okay, we can.
Yeah.
What if you don't crop, you just scale them, make them
I
square?
mean, PyTorch-wise, everything should work.
PyTorch-wise, everything should work. The downstream representations and the expected size of those representations will change. And that will, for clip, for example, will change some of the other logic in the network.
So what if you scale them to be square, rather than chopping off the
Yeah,
side?
so there are different ways to handle this, right? So one way is literally okay, screw preserving distances between pixels or distances in the image. Let's just, warp the aspect ratio and just squish them together to be square. That works depending on how the image encoders are going to be trained. And we're going to talk about that actually in a little bit, because again, I could die on this hill. Another way to deal with this is to add padding on both sides of the image, right? So you have the image that's rectangular, but you're going to pad it on kind of the shorter side to square. This is going to introduce a lot of dead pixels, might be out of distribution for your underlying model, but it also tends to work pretty well and doesn't lose this information more critically. So as long as you're consistent, it tends to be fine. Now, there are also more nuanced questions that I'm going to skip about how the model is trained, right? Questions like whether this training process is more complicated than it needs to be, and simpler questions like should it train longer? Now, asking these questions allowed us to codify the different design space axes in building VLMs.
Yeah, can you go back? Why emphasizing about the parameter side, because Lava uses LoRa, so in all the cases.
So one way to fine-tune Lava models is with LoRa. The actual Lava base model was fully fine-tuned. So fully fine-tuned through the 13 billion parameter LLM. So that
when you use LoRa, the performance doesn't drop that much, at least in the Lava system.
right. So for, let's say, a visual reasoning test, right? Like that COVID test example if you wanted, right? I could absolutely use low-rank fine-tuning, which is a parameter efficient fine-tuning method, that efficiently train this model with a smaller compute budget. Running inference through the model, though, I still have to incur the cost of going through all 13 billion parameters. So for that other kind of persona that I channeled, that robotics persona of okay, I need this model to run, to generate its output in the next 0.2 seconds. 13 billion parameters versus 7 billion versus 1 billion. That makes a huge difference.
The inference,
Yeah. So that's, I think, the reason that I'm going to use specify. Right. So we're codifying the different design axes in building VLMs, which is going to help us build Prismatic, a toolkit for systematically exploring the design space of these VLMs. From these questions, we came up with 4 axes and populated our initial experiments just based on the questions I asked. Now, while the primary contribution of the work was the study itself, we kind of trained 48 different models with various ways of trying to get at, okay, what is the essence of a good VLM? What matters? What is the right image processing scheme? What is the right image representation backbone? I also want to highlight Prismatic as a resource contribution. We built one of the most hackable open source code bases for training different VLMs, one that can easily assimilate new model components and data sets as they become available. This data class, this Python code you see on the right, is literally how we configure VLM training in our code. As you can see, every one of the design axes is made fully transparent and extendable. Now, in addition to a training code base, to kind of measure the impact of individual changes, we also assembled a comprehensive evaluation suite to kind of tie individual changes to the downstream effects. The suite consists of general visual reasoning tasks, so from VQA V2, like general reasoning about images, to reasoning about text in images. So text VQA, reasoning about that sign there to figure out the price of the bananas. To more kind of general visual reasoning, like answering unanswered or figuring out which questions in an image are unanswerable. We also added, again, because of my robotics background, a more targeted set of evaluations for referring expression grounding. So OSID ref here shows up again. We're also going to add like ref COCO, which is a common benchmark for object detection of images. Now this is kind of surprising and cool and crazy to me, right? So the way we're going to treat object detection as a language generation problem is literally by taking these bounding box coordinates and calling like a JSON.dump string as the language output that we're outputting. And we're literally just going to generate that list of floats token by token for the language model. And this works surprisingly well. The third set of tasks that we added were challenge sets to probe finer grained reasoning and other things like propensity to hallucinate in responses. Now, with the combination of our code base and these evaluations, I want to discuss some of our more major findings. Sorry. The first finding we flagged is one of our key questions, like why use clip? So here, the simple question is like, what would happen if we tried fusing different representations that capture the different low-level and high-level features? Then rely on this language modeling objective, right? This text prompt plus text response part to kind of do what the Voltron objective did and kind of blend these two features together and bridge the feature gap. So to test this out, we tried combining two models, Dino v2 and SIGLib features. So Dino v2 is very similar to mass autoencoders in its way of capturing low-level spatial features about a scene. SIGLib is a more modern version of CLIP, trained on a more diverse data set, tends to just generally be better for basically all applications. And the results are pretty incredible, right? So in gray, you kind of have a VLM that's trained with just SIGLib features. And in orange, you have a model that's trained with the fused SIGLib and Dino v2 features that we're literally going to get by concatenating the representations from both models and feeding that to the projection layer. Right? Not only does it preserve performance kind of across the full spectrum of 11 tasks, but it also improves performance on our fine-grained reasoning tasks, the ref COCO detection tasks at the bottom by like over 10% in accuracy, which is huge, like just a free win that we get from fusing these features together. So continuing our exploration surfaced a ton of other obvious results. For example, the suboptimality of resizing and cropping, to more nuanced things about how to properly optimize the model to prevent like collapse in the loss landscape. And all the biggest findings we had were the use of these fused features to get at fine-grained details, and a more optimal image processing strategy that really only works for SIGLib and Dino v2 because of the way that we're trained, right? Literally by warping the aspect ratio. That kind of like preserves all of the information of the image with the simplest possible resizing scheme. And then in terms of data, we identified the importance of code training on LLM instruct data for model safety to prevent toxic or biased outputs, as well as training on math and code data specifically to preserve the ability to generate structured outputs like bounding boxes. Now, these results speak for themselves. In this experiment, in a data and model size controlled setting, we're able to show that we can significantly outperform the base lava models across the board, eliminating some of the unnecessary steps they took to further save on compute. So some examples. This is a picture that I took of the sink in my apartment with some of my roommates' dishes that I cleaned up so they weren't absolutely disgusting for this presentation. One of the questions you can ask, like, okay, which of these objects are dishwasher safe? And surprisingly, like this model is actually able to kind of really nail this and incorporate the external knowledge we need, right? It's able to flag that the dishwasher safe items are definitely the knife and the spatula, but is able to also basically like read that T on the frying pan and basically say that, oh yeah, the frying pan might not be dishwasher safe due to its Teflon coating. This model is also capable of doing fine-grained visual reasoning, right? So if I say detect the blue Yeti mug, and if I checked in the fine-tuning data, Yeti mug, blue mug actually don't appear. Actually, blue mug appears like twice in the data set, but Yeti mug, blue Yeti mug don't appear at all. You're actually able to get bounding box coordinates that literally point to the right object in the scene, framing it in the right way. And then even rudimentary code generation. This is slightly a gimmick because it's probably memorized this, but it's able to generate a fully fledged Python function using OpenCV for basically finding the contours of the white object, filtering by color, and then using that to extract a segmentation. For just 8 hours of training and a fairly small data set, these results are still mind-blowing to me. And it motivates our follow-up work on trying to turn these VLMs into robot control policies more directly. So the idea here is we're going to treat robot actions as text, similar to bounding box generation. One naive way to do this is to quantize the continuous actions in quantize our continuous robot actions and map these to tokens in our vocabulary, right? So one way to represent robot action, so this is a single robot arm, we're moving the end effector around, is to encode continuous actions as changes in your position, so X, Y, Z, as well as changes in rotation, roll, pitch, yaw, as well as like a binary flag for whether I'm activating the gripper, so closing, or releasing an object. To map this into the space of the LLM's vocabulary, all we're going to do is we're going to quantize each of these continuous dimensions into 256 bins, and then map each of these bins onto one of the least frequently used tokens in the LLM. This idea was validated by Google DeepMind in mid-2023, albeit on their own robot platform with in-house proprietary VLMs at huge scales. Now, one question that they didn't answer and that I was really excited about was the potential for these models for efficient transfer, for learning new tasks, fine-tuning these policies to do completely new behavior with fewer than 10 demonstrations or fewer than 50 demonstrations. Something that for most robot learning tasks, we haven't really seen. Now, while I was having these questions, I kind of got lucky in the sense that the timing worked out to create the perfect storm of data, models, and an amazing team of collaborators. Now, while historically robotics data, especially demonstration data, was scarce, Carl, one of my co-authors on this OpenVLA paper, had just finalized OpenX embodiment, a huge data set of over 1 million demonstrations. I think now the number's actually closer to 2 million, of single robot arms and now bimanual arms doing various different tasks. With multiple cameras, here we kind of limited ourselves to single camera third-person views. Collected over 22 robots from 21 universities and research institutions across the world. We also had, through our work on Prismatic, a really scalable code base and the know-how for training different VLMs. Indeed, we relied on this knowledge to build an inference-optimized VLM to serve as our base for VLM training, or for VLA training. So to your question from earlier, right, this is kind of where the inference speed comes into question, right? So we shrunk the resolution of our image encoder down from 384 pixels to 224 pixels, which sped up, which led to huge inference speedups. We also used the Llama-2-based LM to prevent encoding the full system instruction prompt, right? Like, you are a helpful chatbot, please be safe, et cetera, and just start with okay, here is your language model. I'm going to give you an input, predict the output. So no more extra dead space, which let us shrink the frequency of running a forward pass through this model on a workstation GPU, an RTX 5000, to 3 to 5 hertz, which is what we needed for the types of tasks that we were seeing. So while the OpenVLA paper has tons of amazing results showing the zero-shot capabilities of our model to work on the robots that are kind of in the OpenX embodiment pre-training data, I actually want to focus on a negative result that we had, right? Which gets at answering this question that I asked earlier about the transfer potential of these VLA models, which were curiously not as positive as I hoped they were going to be. Right, specifically for single task fine-tuning, VLA models were on average worse than much smaller policies trained from scratch on that data. This is especially problematic given the cost of fine-tuning these models, 5 to 15 hours on 8 GPUs, which is pretty expensive, especially considering you could have collected 10 to 100x the demonstrations for a fraction of that cost. Now, on language condition tasks, the story is a bit more positive, but still not as conclusive as I would have liked it to be. Now, one thing I do want to pull attention to, though, which I'm really keen on exploring more, are the pink lines in the graph, corresponding to an OpenVLA model from scratch. In other words, starting from a base VLM and just fine-tuning on these small demonstrations.
So how are you differentiating how are you defining narrow single instruction versus multi-instruction?
So on the left side, flip pot upright is the only task we're fine-tuning on.
Okay.
All the model is expected to do at the end of the day is flip pot upright.
Yeah.
On the right side, knock object over has 3 different categories. So knock the banana over, knock the plate over, knock the table over. Right, so it's multitask, but in a limited setting. Right, so important result that I want to pay attention to are the pink lines. Right, so this corresponds to starting from the base VLM, the base prismatic model from scratch, skipping the 1 million or so demonstrations of robot data that we trained on, and just going straight to training on these 50 demonstrations. While those results aren't perfect, they also aren't zero. which makes me really excited about the potential of this class of models moving forward. Okay, so we're running a little low on time, but this combination of work on embodied perception and building VLMs and VLAs represented the bulk of my PhD research towards building foundation models for perception and action. Now, this last part of the talk, I want to transition to our second principle, sustainability, and actually push these ideas forward into building and deploying collaborative robots with real people. I mean this quite literally. Like, I cheekily motivated the part of the talk at the beginning by trying to reproduce this video clip from the first Iron Man movie. The actual scientific motivation was much more crisp. Right? I've spent the last 6 years of my life working at the intersection of learning and human-robot interaction. And I've borne witness to so much progress. So the goal of this project was really to assess the viability of these approaches for real-world applications. The are we there yet moment for robot learning. And more importantly, I wanted to find different scenarios where our expectations as stakeholders diverge significantly from robot capability, not only to inform my future research, but also to get a sense of how far we are from that future. So to do this, we designed 2 scenarios for evaluation. In the first, we built a controlled gift bag assembly line task. Here, the goal is to engage with non-expert users with minimal ML expertise to do a repetitive task of assembling 4 gift bags in a row packed with the same objects. To encourage collaboration, we also had each user write a pretty lengthy handwritten card to attach to each of the bags. The hope here is that a good collaboration is one where work is parallelized effectively. And in the second scenario, which you already saw, we focused on stop motion animation, using the robot as a controllable camera arm. Here, the goal is to see how far experts, namely me and my co-author Jen, are able to scale the system for more complicated and freeform tasks. So in trying to tackle these settings, we asked ourselves an important question, which is like, what do we minimally expect of collaborative robot systems? Right, the first property we came up with was that of transparency. If we put ourselves into the shoes of a user working in this gift bag task, what does that look like? Well, given an instruction like, can you grab the jelly sandwich thing? It's not only getting a sense of what the robot plans to do, but to be provided with an interpretable trace that explicitly links the instruction I gave to the action the robot intends to execute. In this case, a segmentation mask around the right object in the scene. And you can see kind of in the picture that the user is able to have a monitor that kind of shows this graphical user interface to them in real time. Furthermore, if we ask the robot to do something it's uncertain about, we wanted a way for our system to vocalize that uncertainty, telling us exactly why the robot was confused and how to resolve that confusion moving forward. The second property we came up with, adaptivity, follows pretty naturally. It's the real-time teaching component I talked about at the beginning of the work. For example, if the robot doesn't know how to execute a given behavior, the user can opt to teach it through decomposition, breaking the initial instruction down into simpler steps.
What does it mean that it doesn't know?
What does it mean that it doesn't know?
Yeah.
So from a language perspective, it's a question of, am I able to parse this into a valid plan? And we're going to talk about exactly what the system looks like in a little bit. From a vision perspective, it's like, oh, can I find the right object, or did the user intervene? From an action perspective, is literally, is this
It's going to find
plan?
some object, whether or not it's right.
Yes, and then the user has to basically confirm and check, like, oh, that's the right object. And similarly, like for executing actual robot actions, like trajectories, we show them in simulation a trace of what the robot is going to follow. And if that doesn't look right to them, they can also.
So it's not as if the robot's really saying, I don't know how to do it, it's that the plan is unintended, the user does not like the plan.
So it is not always going to produce a response, right? The language model has the option to basically say, like, I don't know how to do that. And we prompt the language model to do that. So in that case, it's very clear, like, okay, I don't understand means that the model is choosing. I don't understand. There's also the user-gated component, which is the verification step. It's like, this is what I'm going to do. This is what you wanted, right? Which is like a very quick, like, look up at this screen, like, okay, yeah. So to teach new behaviors, you can teach through decomposition. So break down the initial instruction into simpler steps. Now, crucially, the robot should be able to integrate this teaching example immediately, as soon as the next instruction. Now, furthermore, if the robot knows what behaviors to execute, but is missing something lower level, like where to find the toy car mentioned in language, we want to be able to vocalize that uncertainty as well, and again, prompt the user to provide supervision. In this case, by pointing or clicking on the object, on the GUI. To build robots that exhibit these properties, we designed Vocal Sandbox, a framework for building robots that can adapt and continually learn from these types of real-time interactions. The key idea is to embrace transparency through structure and modularity. Right? Rather than learn an end-to-end policy, we're going to map instructions to interpretable programs that help users more reliably understand a robot's behavior. right? So teaching is going to take the form of providing supervision for teaching new functions and arguments from different types of multimodal interactions. And to start, and Matt, this gets at your question, we're going to assume this base API with typed functions, literals, and predefined submodules. So you can see a quick mock-up on the left. We have access to a VLM and a robot that can execute these primitive skills, as well as a few predefined behaviors and objects. Now, when asked to grab the jelly candy thing, what actually happens? So we're going to have a large language model. This work we used GPT 3.5 Turbo to encode this API as part of the prompt, and then have it generate a satisfying program or abstain, basically saying like, I don't know how to do this. Right. So in this case, it generates a plan for detecting the candy, going to it, and then grasping it. And once we've generated the plan in language, so like the language model planning always happens first, then we execute the vision part of the problem. So here, our VLM is going to try and execute any of the relevant submodule calls, returning as output these interpretable traces, the highlighted segmentation mask to provide the user with more insight. And then finally, action is the last step. We're going to feed the resulting groundings and plan to this action module that's literally going to show the user in simulation what the robot's going to do, ensuring transparency at all points in the interaction. So to make teaching more concrete, I want to step through an example of what it looks like to teach PAC. So starting with, okay, the user asks the robot, pack the candy. Robot says, I don't know how to do that. Teach me. User says, I'm going to decompose it into these steps. Model is able to decompose it into these steps because all of these steps already exist in the API. After I have provided this decomposition, I'll just set a flag saying like, great, that looks right. And this is going to trigger the synthesis step. So here, we're going to synthesize a new function for kind of representing this idea of packing an object. Right? We're going to prompt our language model, which has seen the entire chat history as well as like every iteration of the API throughout the episode, and have it synthesize that function signature, right? The name of the function, its type signature, and also that doc string that we're going to use to like tell users, oh yeah, this is actually what this function means. And then for the function body, we're going to just use a simple heuristic to kind of lift the function body up from the decomposition, subject to the function signature. This allows for so crucially, these functions are immediately added to this API once they've been synthesized, and they can be built on in further teaching interactions. This allows for large amounts of expressivity through compositionality, teaching more and more involved behaviors that break down to longer sequences of primitives. So I want to give you an example of this from one of our users in the user study. So in this video, the user's already defined pack and a higher level behavior for assembling the entire gift bag. This is what his interaction looks like. Right, so as you can maybe see on the GUI, maybe it's a little too small. It's generating this plan, assemble gift bag, which decomposes down into 3 calls to pack objects for the 3 objects that need to go in the bag. Every so often, it's going to highlight an object, and he's going to like occasionally look up confirm. But in the meantime, he's writing his card. Collaboration is proceeding as expected. So we evaluate this variant of our system through a long horizon user study with 8 subjects, each spending 3 hours with the robot with 3 different missions for the task of assembling these 8 gift bags. We're going to compare this with 2 simpler systems, right? So the static variant of our system that only has access to the base API, right? You can think of this as like kind of what like an existing semantic parsing system or an existing like language model planning system might do. As well as a model that can only allow for teaching through language instructions instead of allowing for like defining lower level like objects or behaviors through gestures or clicks. It's kind of breaking the multimodality. And then to evaluate the adaptivity of our system, we're going to look at behavior complexity over time. For the instructions that I'm giving at bag 1, bag 2, bag 3, on average, how many of my primitive sub-functions am I executing? Now, for both of these that we see, for skill failures, like the vocal sandbox system has much fewer failures because it's able to teach new objects, it's able to teach new motions. For behavior complexity, we're able to show that by the 4th bag or by the 3rd bag, we are steadily improving and increasing the number of primitives that are executed per instruction, right? We're executing more and more complicated behaviors over time. We can also look at collaboration efficiency through a flame graph, right? Of just like this is for user 4 in our user study, looking at the time spent instructing, which is just like looking up and confirming what the robot is doing, versus parallelizing, which is like where they're doing work async, not looking at the robot and writing the card.
Sorry, I missed it. So is there any adaptation if you go back? So initially I thought the blue was an ablation of adaptation. but it looks like the behavior complexity is going up. So there's some adaptation going on.
Yeah, so you do have like just some ability to say like, okay, so if pack is just a combination of go to, grasp, or pick up, grasp, go to, drop, I can still learn that from my language model. The adaptation that I can't learn is like, okay, if there's a new object that I want to pick up.
So how do you learn that? You just query the language model. I don't understand pack. Can you break this down for me?
Yeah, exactly. So looking forward, I'm really excited about Vocal Sandbox and in general the potential it has for providing utility for different types of people. Concretely, we're actually in talks with local Bay Area bakeries and cafes to use our system to help with time-intensive tasks, like portioning dough, cutting vegetables, mixing batter, or just like moving heavy objects around, right? Things that aren't like sexy, they're not like folding your laundry and like a one end-to-end.
Is that sexy?
End-to-end shot, or like super useful, like very targeted things that are actually providing meaningful utility to a specific group of people at a specific time, reliably. So basically, stay tuned if you're looking for a robot sous chef. Okay, so I'm a bit over time, but I'm going to quickly wrap up with kind of just some of my broader research. So, broad strokes. I use language as this core mechanism to build robots that learn from and work with people. I do this through these two axes, capability and sustainability. Under capability, we talk a lot about my work on learning for perception control, building these foundation models for effective visual reasoning, effective action prediction. What we didn't get to talk about is some of my work on data creation and analysis, right? Like what matters when collecting data for robot learning and embodied understanding? How do we identify weird pathologies in our data sets? How do we probe what is good quality data, what is suboptimal data? On the sustainability side of things, we talked about some of the work on adaptation and learning. I've also worked kind of with the HRI community a lot, looking at things like corrections. And more specifically, work on intuitive human-robot interaction. Right? How do we reduce friction in human-robot interaction by designing better assistive devices, telling robot demonstrators like, oh, the demonstration you provided isn't great for this reason, do this instead, or encouraging proactive behaviors. Like, okay, as a robot, I can take more initiative in this session. Looking forward, I'm really excited about things like building adaptive and transparent VLAs, right? Something that we didn't see in the Vocal Sandbox work, right? So consider this training task, here's a VLA. What's cool about a VLA is that we get to model these views, arbitrary views of text and images, right? Anything that looks like text or looks like an image is fair game as input to the VLA. What that lets us do is that like at deployment, I can collect interventions, right? Like I can point at an object to predict the bounding box, or I can like click on it and like an iPad or a GUI. I can also provide corrections, played by the dish rack. I can scribble out parts of the scene that I don't, want the robot to go to. I can draw a path like that I actually want the robot to follow. This is cool because it lets us kind of like train this more adaptive VLA that's able to condition on these corrections, these bounding boxes, and SVG representing the path that the robot should take, as well as these overlays, right? These sketches on top of a scene. So we can get at adaptivity by conditioning on these interventions. We can get at interpretability by forcing the model to generate these traces ahead of actions, right? So kind of like O1 or these more reasoning LLMs, forcing it to generate a chain of reasoning steps ahead of time. Eventually, you might want to actually use these reasoning steps to explicitly verify robot behavior ahead of time. And then distillation, right? Distilling intervention means back into the VLA to kind of enable better autonomous performance over time. Finally, ecologically valid data collection for robotics. Take a walk around any of these big startups or research labs that are trying to scale up imitation learning. Take a look at Tesla's Optimus warehouse. You see something like this. You see a bunch of disparate stations that are each trying to do different tasks that are trying to exercise some cool new ability, right? So on the left, we're doing something with food, with plating. In the middle, we're doing something with like small scale tools. On the right, we're doing something with deformable objects like cloth. Tasks that by themselves are really cool and show like, okay, what are the limits of robot capability, but aren't really related. Right? And so I'm going to have a hot take here and say that the hardest problem in robot learning is how we choose that next task. And here, I really want to start working on ways to kind of build more natural curriculums, right? Building a rhetoric, a story around the data that we're collecting in the world, right? If I'm deploying a robot in my home, let's start by having just unload the dishwasher. Then let's rinse plates. Then let's go from plates to, rinsing cups, mugs, then to arranging tables. Building out this natural space where we can actually start probing some of these broader questions. Questions like scaling laws, right? Like how can we better get a sense of cross-task transfer? Going from that hardware example to the cloth example, why would I expect that to work, right? They're completely different tasks. Why should I expect positive transfer? when should I expect possible transfer? And then ultimately trying to get to this place of real world deployment. All right, I'm gonna end there. But if there are any questions, happy to take them now.
So we have time for maybe one question, because I know we're over and people are waiting
I
for
have
the
a
room.
quick question. So I noticed a lot of different cases where you could have lots of different. I was just wondering, so how do you think of generalization in this? Like, and so what kinds of things would you consider when sort of has there been work, or have you thought about like what's the taxonomy of generalization problems that would be interesting? So there's like generalization enabled by language. There's generalization about different spatial orientation. How have you been thinking about these?
Yeah, so I like to, I'm gonna respond to your question by framing this against local sandbox. So there is compositional plan generation, right? Executing scene behaviors, maybe with new objects, but realistically just combining different skills that I've learned in different ways. I think that's what we've started to see the most of in the last 2 years of robot learning research, right? Using kind of LLMs as planners, using VLMs as planners. The next category is actually the hardest, which is behavior generalization, right? I have learned maybe to slice vegetables and peel potatoes. Can I generalize to a new motion that is somewhat similar, that kind of has aspects of both peeling and slicing, right? Like screwing or like peeling it, or like cutting into an avocado and avoiding the pit, right? Again, with the feeling that I have in my head. That's really hard. I haven't seen a lot of work that does that, but it's something that like we really need to get towards. And it's something that I think that some of these, vision language action models, better data collecting can get us to. The third level is now, again, kind of something that you see a lot more of, and a lot more of like very early in my PhD. And this is like just visual generalization. Robustness to different visual features, it's like different like camera shifts, different lighting conditions, different colors for objects, and things like that. Right, so that you've seen a lot more of. Right, so those are the aspects that I'm thinking of, but I'm also limiting those modalities to like language vision and action.
Sure. Yeah.
Right. I think to actually solve robotics, we're going to need things like tactile sensing, audio sensing, and there that introduces other types of generalization that we might care about. So it's a hard and large question. Great, thank you.
Yeah, cut it there. Let's thanks Sid again.